everyone, welcome back to this video. In today's lesson, we are going to learn one of the most powerful theorems in vector calculus, which is Stokes theorem. But before that, we are going to explore this together with my teammate, Nuna, Widat, Indo, Wani and me, Vida. So you've probably heard about Green's theorem, right? So Stokes theorem is just like their big siblings. Stokes theorem connects line integral and surface integral in beautiful and practical way. By using Stokes theorem, we can calculate the curve of the field and the surface covered by the curve. So in this video, we are going to learn how to calculate Stokes theorem and what are the real-world applications that can be solved by using Stokes theorem.
Nuna? Thank you.
This is Nuna, the smartest student in the class.
Widat?
And this is Widat.
Thank you. Nuna, you got full mark.
Oh, nothing to surprise.
I don't understand anything about Stokes theorem. Can you teach me?
Of course can. Like this.
Okay, with that, since you're not so confident to use Stokes theorem, let me walk you through this example question slowly and nicely. The question wants us to evaluate this line integral around C circle of x square plus y square equals to 16 at z equals to 5. This circle is oriented counterclockwise. Instead of doing the line integral directly, here we can apply Stokes theorem using this formula. This formula needs three things, which is the limit, the curl f, and the del of z minus fxy. And that is exactly what we are going to do. For the first step, we need to calculate the curl f. And here, we just do the usual determinant thing like this. For the first component, we will get x exponent xy minus 2x. And for the j component, we will get y exponent xy minus y. And for the last component, we will get 2z minus z. And to simplify, we will get x exponent xy minus 2x, y exponent xy minus y, and z. For the next step, since our surface is a flat disk at z equals to 5, the normal vector is literally just pointing straight up. So, our del z minus fxy is 0, 0, 1. And moving to the next step, we need to determine the d of s on the xy plane. But again, since our surface is already flat, so the projection is just this circle with the radius of 4 from x square plus y square equals to r square, and the given equation is x square plus y square equals to 16. That's where we got r equals to 4. And here we can use polar form to come out with the polar equation, which is x equals to r cos theta and y equals to r sin theta. And we can also come out with the polar limit, which is for the r, we can get 0 from 2, 4, and for the theta, we will get from 0 to 2 pi, and for the dA, it is equal to r dr d theta. And for the last step, where we put everything from step 1, step 2 and step 3 together. So we will come out with for the limit 2 pi 0 4 0, and for the curl f, x exponent xy minus 2x, y exponent xy minus y, z dot, we'll get 0 0 1 r dr d theta. So here we just take the k component because others we will get 0 when we expand it. Yep. So we can simplify 2 pi 0 4 0 z r dr d theta. Our z is equals to 5. We also can come out with 2 pi 0 4 0 5r dr d theta. And for the final touch, we integrate 5r first. 4 0 5r dr d theta. And we will get 40. And continue, integrate over theta, and we will get the answer after we integrate. The final answer of this question is 80 pi.
Wait. I cannot visualize this in real world.
Let me think. Oh, look at the circle. Right?
Nuna! This circle?
Yes. Now, look at the blue surface. That is the S plane. And the red boundary is our C boundary. With that, do you feel the air around you?
Yes.
So, using Stokes' theorem, we can calculate the air circulation in that circle.
Wow, really?
Yes, because the air circulation around a boundary curve C equals to the total curl across the blue surface that the red boundary encloses.
Oh lah, easy je. Okay, let me try question number 2.
So, for questions number 2, we use Stokes' theorem to evaluate FDR, where fxyz is given and the curve is also given in the xy plane with counterclockwise orientation, looking down the positive x-axis. So, our goal is to compute FDR. Instead of doing a direct line integral, we will use Stokes' theorem because it is much simpler. This is the formula of the Stokes' theorem. This converts a line integral around a closed curve C into a surface integral that has the curve as its boundary. It is a very important tip that the orientation of the curve must match the orientation of the surface by using right-hand rule. So the first step is we need to calculate the curl f. By given formula, we use the determinant formula. So to calculate the I, we need to cross the first line and column to get the answer for the I. So we will leave out for this and we'll differentiate by cross them. Here we got here, and same goes to J. J we cross this J and this is what remaining, and we need to differentiate by the cross that, and it will give to this. But we need to look for the symbol by using the determinant sign that show us plus minus by minus and minus plus minus, if you remember that. And after that, for the k is the same like before. You need to cross this, and this is what remaining, and differentiate the others, and you will get this, and end up the answer is this. Moving forward for the steps 2. As we know, C is the unit circle in the xy plane, so the easiest surface is simply to plot this. Since the curve is counterclockwise, when viewed from the positive x-axis, the correct normal vector is pointing upward, and the vector is n001. So we use a convenient surface S for simple calculation. This is given, and z is equal to 0 because of this direction, and n equals to k. For the third step, since our surface is already flat at z equal to 0, the projection is simply the unit disk, which is this one. This is region over which we integrate when calculating the surface integral. By this, we can simply find the r, which is r is equal to 1. As we convert in polar form, we get that x is r cos theta and y is r sin theta. The limit for the r is from 0 to 1, and for theta is 0 to 2 pi because this is a full circle in the xy plane. So for the fourth step is we evaluate the surface integral by using this formula. So we use the dot product formula, which is we simply put the value, and we need to multiply each and add up for the each I, j and k, and the last answer will get the scalar value, which is a 1 value, not in vector anymore. And yep, we will get 3 and integrate the dA. And now we can find the answer by putting this dA equals to r dr d theta in this formula. And we need to integrate like how we integrate before. So we need to integrate r and get this. And also this is a step by step how you integrate. And the final answer for dr is 1 over 2. Then we integrate for the theta, and the final answer you will get is 3 pi.
Like that? Yeah, you get it now. Yes.
With that, we can wrap up our lesson on Stokes theorem. We have learned that Stokes theorem connects line integral and surface integral through curve of the field. It is an amazing tool that not only simplify our calculation in vector calculus, but it also helps us in understanding the real-world applications such as airflow, electromagnetism, and so on. If you understand what Stokes theorem truly represents, then you are one step closer into mastering vector calculus. That's all from us. Thank you for watching.